Okay, in this video I'm going to continue on with my tutorials on thermodynamics and statistical mechanics. So this is video number 32 and I'm going to begin a series of sub-videos on the two-state paramagnet. So the previous video to this is number 29 where I discussed the heat capacity or constant volume, how to calculate the heat capacity at constant volume, and I'll recap on that in a moment. And what we did was, in a lot of previous videos on the Einstein Solids and ideal gases, we performed the series of steps which I outlined in video number 29, even though I didn't actually say that we were doing it. So we're going to do that exact same process this time to a two-state paramagnet, because the system is more complicated and has some very interesting behavior, and it's it's counterintuitive, but it's a good idea to look at this and to try and understand this difficult behavior, or this different behavior in terms of thermodynamics. So we saw in video number 29 that in order to calculate the heat capacity at constant volume, we need first of all to get some sort of functional form for the multiplicity. Then we were able to get the entropy, which we know is equal to Boltzmann's constant times the natural logarithm of our multiplicity. Then what we did was we plotted our entropy versus energy graphs. We know that del S del U, or the inverse of the slope of our del S del U, or entropy versus energy graph, is equal to temperature. Now once we have temperature, energy and entropy, we're able to get the functional form of our energy in terms of the number of particles, the volume, the temperature and whatnot. Now we know that the heat capacity then is going to be very easily calculated, because it's going to be del U, del T at constant N and constant V. And that's what we're going to do right now. Now I'm going to do it in two ways. In this video I'm going to do it numerically, and in the next video I'm going to do the whole thing analytically. So we'll actually come up with the functional form for the heat capacity without any numbers. But in this video it's definitely going to be all with numbers. Now a recap on entropy versus energy graphs. We saw four different types of energy versus entropy graph. Okay, so each of these are energy versus entropy. So that's entropy versus energy graphs. Sometimes I get confused, but this is correct. So we could look at this behavior here. So we know that T is equal to del S del U, or the inverse of that at the very least. Alright? So if you look at it here, the slope, which is del S del U, in this case is very steep. So we say that the slope here is steep, and as a result T is low. So if you have a steep slope, your temperature is low and it wants energy. Okay, and this is a normal system. We know that cold systems want energy. That's what we would consider a normal system. Then look at a system whereby the entropy versus energy graph is constant. So here T is constant as the energy is increased, so we're looking at a phase change. This is a phase change. Alright? So next we had a graph that does this. So here what we can see is that we actually have a shallow slope. So this time T is high. Okay? This time T is high. So it doesn't want energy. It does not want energy. Alright? So it does not want energy. So we can say, for example, that its temperature is decreasing as you add energy in this particular case. Okay, its temperature is decreasing as you're adding energy. Okay, now the final one, and this is the one we're going to be seeing in this particular video, is when it does this. So in this particular case, the slope of the graph is negative, which means that the temperature is going down. So as you add energy, temperature is going down. Now, where does this happen? Well, that would happen when, for example, your energy is going into, it might be going into kinetic or into potential energy rather than to kinetic energy. So in this case, the slope is negative, and we get a negative temperature. All right, and that's very important. Now that we need to understand that. So in general, increasing the temperature corresponds to decreasing the slope of our entropy versus energy graph. So the graph for such an object is everywhere concave down. So if we see concave down like this, we know that it's a low temperature and it wants to gain energy. Alright? So when we see that it is concave up like this, we know that as we add energy, the temperature in actual fact is going down. And the reason it's going down is because the energy is going into other things such as potential energy. And finally, well, we know this one, we won't talk about the phase change, but finally, and this is the important one, that the temperature is actually decreasing as we add energy. And this sort of system would have a negative heat capacity, and that is perfectly acceptable. And in actual fact, as we will see soon, that is the case of a two-state paramagnet. Now, I don't want to get into the physics of a two-state paramagnet. What I will say is as follows: we have two ways of looking at a paramagnet, right? So you have magnetic dipoles. So if you have your magnetic field, well, the magnetic dipoles can either be up or down. You can think about it like electric dipoles, so you spin up or spin down. Okay, so this would be the magnetic field. Now this would be and these would be our magnetic dipole moments. Okay, so the magnetic dipole moments, the down in actual fact has the higher energy. So this is, we say, plus mu b, where b is the field and mu is the proportionality constant. Okay, and this one here is minus mu b. So in actual fact, when the dipoles are pointed down, it has a higher energy. Right, I'm not going to go into the physics of it. I'll just accept this for the moment, where mu is our proportionality constant. All right, so let's think about the energy of our system. Well, if you look at the energy of our system, well, U is going to be equal to the following thing. Well, in general, the energy is going to be mu times B. Now we need to find out how many dipoles we have. We know that if some are pointing up and some are pointing down, well, the total energy is going to cancel. So it's going to be the number down minus the number up. And the reason it's that way is because when the magnetic dipoles are pointed down, they're actually at a higher energy. Or we can rewrite this as mu b outside of the total number of dipoles minus twice the number of dipoles pointing up. Okay, so I'm just writing it in terms of one of the numbers of dipoles. So dipoles pointing up. Now, what about the multiplicity function? Now, if you think about it, this is a two-state system. It can either be up or down, full stop. So if you go look at my videos on Einstein Solids, we know that the multiplicity of a two-state system, which we did, and I guarantee you we did this, so I'm going to say if it's going to be in the up state, it's going to be equal to the total number of dipoles, factorial, and then we have n up factorial and down factorial. Okay, and look, you can check that out yourself, or just take my word on it. I hope you take my word. So now what we actually have is, we have the functional form for the multiplicity. So we want to calculate the heat capacity. So we know what to do next. We need to take the entropy, which is K times the log of the multiplicity. Then we plot our entropy versus energy graph, and whatnot. Now, I'm not going to bore you with that, but what I will do is give you the answer. So let's go plot our entropy versus energy graph. And I did this numerically, or this was done numerically, we'll say, right? So we have entropy in units of Boltzmann's constant, and we have energy in units of mu times b. So this is U is equal to 0, we'll say. Alright? So this area here is negative energy, this area here is positive energy. Now, how can the system have negative energy? Well, I told you that when the dipoles are pointed up, they have negative energy. When the dipoles are pointed down, they have positive energy. So this, we'll say, is up, and this one here is down. Up and down, or dipoles pointed up, dipoles pointed down. So if you plot this, you know, if you look at the figures and you plot it, you're actually going to get something like this, which is a bit odd. Because if you look at it, think about the four graphs we saw earlier on. If you look what I'm blocking out, ignore what I'm blocking out, and on the left hand side we know that is a concave down system. So it has got a low temperature and wants to gain energy. This here is, that's concave down, but this is also concave down. But in this case, as you add energy, the temperature is in actual fact decreasing, so it's got a negative heat capacity. Alright? So that's a bit odd. We're actually after seeing a system that has this strange behavior. As you add energy, the temperature actually goes down, which is very strange. Okay, so the largest multiplicity and therefore the largest energy occur at u is equal to 0, when exactly half of the dipoles point down, and that makes perfect sense. You have half pointing up and you have half pointing down. So thereafter, if you add more energy, the multiplicity and the entropy actually decrease, since there are fewer ways to arrange the energy, which should make, that should make more sense. So we can see here that the entropy goes down in actual fact after we pass the zero of energy as we add more energy. So suppose that the system starts out in the minimum energy state. Well, negative energy corresponds to up dipoles. So let's say all our dipoles are pointing up, and this is the minimum energy state. Okay? Now, here the entropy versus energy graph, as we see on the left hand side, is very steep. Steep means a low temperature and it wants to absorb energy. Okay? So as the energy increases, but of course the energy is still negative now, so this is negative E, this is positive E. Okay, so as we add energy, but we're still on this side here, we're adding the negative, or the energy is still negative. Okay? So the entropy versus energy graph becomes shallower, so the tendency to absorb the energy in actual fact decreases. So this is just the exact same for an Einstein solid. However, if we look up here, so when it gets to the 0 of energy, in actual fact the slope is infinite. Okay, so the temperature, that tells us at u is equal to 0, T is equal to infinite, or infinity. That's a bit strange now, I think. So what we'll suggest is we'll just accept that. We'll accept that the temperature can be infinite, or for our definition of temperature, in this particular case, it's infinite. Right, so what does that mean? Okay, so it means that the energy of the paramagnet goes to 0, so the slope of the energy versus entropy graph goes to infinity. So basically the tendency to absorb more energy is after disappearing. The system doesn't care whether or not it absorbs or it loses energy. Okay? Now, if we add a bit more energy, it behaves very unusually, as we can see here. If we add more energy, now the system doesn't care what happens. So if we still add more energy, the slope of the entropy versus energy graph becomes negative, so it will spontaneously give up energy. Okay, so the temperature is going to decrease, it's going to give up energy, okay, to any object. Alright, now why would it give up energy? Well, it might give up energy if the object it's giving it up to is going to increase the overall entropy of the world, or of the universe. So that's a very possible scenario. Okay, now, it's supposed to be a y as well. Now, think about it now. So, the temperature is the reciprocal of the slope of the entropy versus energy graph, and it increases as energy is added. Okay? But when u is equal to 0, the temperature, as I said, is infinite, meaning that the system will gladly give up energy as it will gladly give up energy, I suppose, to any other system whose temperature is finite. So it's a strange thing. We have this thing called infinite temperature. Okay, so and at even higher temperatures we have higher energies. We seem to have this negative temperature. So it seems that we have positive temperature on the left hand side, and yet we have negative temperature on the right hand side. Now, this is a bit odd, that's why we're doing it. Negative temperatures are actually hotter than positive temperatures, and they can only happen in closed systems. Now, I really don't want to get into it, but we'll just accept that you can have negative temperatures in closed systems, and when you do have them, they are in actual fact hotter than positive temperatures. So the temperature, as it increases, goes from positive to infinity to negative, and that's the temperature getting hotter. Alright, so yeah, I think we're doing okay here. Now, what happens if we think of the heat capacity of our particular solid? And once again, this is done in a numerical way here, and I'll do it in an analytical way soon. So let's plot the heat capacity at constant volume in units of N times K versus energy, KT, in units of U times B. And it looks something like this. It looks something weird like this. Now note, so the whole point here is that the example of the paramagnet has negative temperatures, and another is quite unusual behavior. So the whole point of this is that we need to think about entropy rather than as temperature, because temperature is the less fundamental quantity. Alright? So now let's think about our heat capacity. So let's just take it that this is the heat capacity if you plot it. So note that the heat capacity goes to 0 as the temperature goes to 0. So that's required by the third law, and we're happy enough with that. Okay? So what else can I say? Also, the heat capacity decreases as the temperature increases. So it's got a very large dependence on temperature. Okay, it's got a very large dependence on temperature. And if you remember when we did Einstein Solids, there was no dependence on the temperature, or the heat capacity at constant volume was temperature independent. Whereas in this case, it is temperature dependent. Okay, because we saw we could have negative heat capacities. So that's the point here. We want to think about entropy rather than as temperature, because the temperature can be negative. We want to actually understand the behavior of our system by looking at our entropy versus energy graph, and that's what I'm going to continue on doing in the next video, where I'm going to do an analytic solution. So thanks for watching. Please pass it on to your friends, subscribe to my channel, and if you're in a good mood, you might also click on an ad. Thank you.